respiratory patients, or was it pretty different from patient to patient?
It was different from patient to patient. However, the basic pattern, I would say, similar, but because of the different morphology of left atria, you can imagine that, when your pulmonary veins come really close together all of a sudden, or they merge and things like that, that you're going to have differences. But I would say, I can show you the paper that there was a transmural change in the fiber direction in the atrium. Oh yeah, these things are like 140 microns or something. These pictures, they're just crazy.
Yeah.
After class, I'll pull up the paper. It's nuts. Well, I mean, 4 days on an MR scanner with a heart in a jar. Okay, so motion not a problem, signal to noise not a problem, because we got 4 days. Basically with MR, as we'll see, signal to noise goes as root scan time, right? So if you need smaller voxels, you just need more scan time. And so to get voxels the size of a CT, MR requires about a day, right, to image, something like that. So what we're going to look at now is the beginning of MR. And I can't say enough good stuff about MR. I did this since the late 80s. I started doing cardiac MR. And it's a remarkable achievement in that people really put a lot of engineering effort and a lot of development into making cardiac MR work, right? It's something that, when you look at MR, most things that you want to do with MR, like musculoskeletal and brain and functional MRI, everything's pretty static. You can hold things still. Heart, not so much. Patient's breathing, heart's beating. You require minutes to take the data. So how's that going to work, right? And so a lot of effort went into self-correcting acquisitions that throw away bad data and keep good data. And also designing coils like this one, where you have a massive coil array around the patient's chest, and you might have 6 coils on the top here, 6 coils on the bottom, so that it's really lighting up the appropriate spot. So as we'll see, this coil here, it's going to be receiving radio frequency signals from the patient that are on the orders of millivolts, microvolts. So it's a very small signal coming out of the patient, but you put coils close enough, you can hear it, you can listen for that. And in doing cardiac, normally you have a box like this sitting beside the patient where they're hooked up to an EKG such that you can trigger or at least sort where your data has been obtained in the heart cycle, because you're going to be using hundreds of heartbeats to put this data set together. You need to know where everything is in the heart cycle, and so you try and get a really good EKG. Just like CT, you will also inject contrast sometimes, and so there's normally a power injector sitting beside the scanner, and the timing of the injection is important as well. So very much like CT, the scanner itself, the bore is usually smaller than a CT bore in the sense of diameter is smaller, and it's longer. The cylinder is longer, and so it presents problems for people who are claustrophobic, because when you put their heart in the scanner, normally their head is inside the scanner as well. And when you are lying on an MR scanner and looking up, and they put you in, you are all of a sudden looking up at something that's about 6 inches away, right? And for some people, very uncomfortable, right? They don't like it. You can watch their EKG change as they're being rolled into the scanner. So they might start out with like 72 beats a minute, and then when they come to a stop and they've been in there for 15 seconds, they're up at 100 beats per minute because they're so nervous. So you can take care of that with Valium sometimes. If you give people Valium before that, they'll relax and things will go okay. Other people, it's just not going to happen, right? So, but for the most part, Works out okay. The other thing about MR is this patient, you know, he has headphones on because the scanner is quite loud. So one, it protects their hearing. Two, they need to listen to instructions. And the instructions are about breathing. So the MR, you usually get them to breathe 3 times rhythmically and then hold your breath. And they usually hold their breath around 10 to 20 seconds, depending on what kind of acquisition you're doing. And some people are good at holding their breath, others not so good. When I was a graduate student and a young faculty person, and I was highly motivated to get really good MR data, I could hold my breath for 2.5 to 3 minutes, right? And just hold your breath and just, you know, this paper's getting published. It's just we're gonna make this data good. And you can do remarkable things when you can do that. With people who are suffering from cardiac disease, not so much. They, you know, volunteers can do it for like 30 seconds to a minute, just normal volunteers, and highly motivated people for more than that. But patients, not so much. But the data is fantastic. I mean, when everything goes well, this is a cine loop, probably obtained with, so you can see the voxel sizes here are about 2 by 2 by 8. So let's take a step back and remember what CT is. CT is 0.5 by 0.5 by 0.5, right? So we got a factor of 16 here. We got a factor of 3 here. So the resolution is of a different ilk. However, you know, you don't see as well all that trabecular detail and everything, but you know, you do see the function remarkably well, right? You see the, you know, the change in the conformation, the tissues. This white signal up here is fat. Remember, the coronaries reside in that pad of fat on the anterior wall of the heart. And so these things there are the coronary vessels. So in the middle of the vessel, you get a bright signal from the contrast that's in there. And at the wall of the vessel, there's a partial voluming of the fat that is outside with the muscle / you know, vascular wall tissue. And those signals cancel each other out, so you get a black signal there. That's called partial volume fat water cancellation. And you can see that's happening a lot around here too. This is fat. This is fat right here. This is liver, okay? And, you know, the field of view is good. We've got the whole heart in a 2D view. The problem is all of this data was taken in one slice over the course of 11 heartbeats, say, right? And so you have to move, then you ask the patient to hold their breath again, and you do the same acquisition in a slice that's displaced by 8 millimeters, you know, orthogonal to this direction. And and so now you're stepping through the heart on these 1 centimeter, 8 millimeter steps. And if the breath holds are different, that the heart shifts around as you move. So it makes 3D stuff a little arduous. And you know, if you ask somebody to hold their breath for 11 seconds, when can you ask them to do that again? Usually you give them 20 seconds, or something like that. So you get data every 30 seconds, something like that. You can, because of the way MR works, you can obtain data in any orientation. So here's another 12-second breath hold with the same voxel size or same resolution. And we've rotated the acquisition such that it is a plane cut through the heart and along the long axis. So you can choose a 4-chamber view, right, just by manipulating your gradient pulses such that if you want to look at that 4-chamber view, you can. So that's a terrific thing as well, in that you don't have a tech trying to figure out, is this the right 4-chamber view with a transducer on the chest wall? You just type this in based on some scout scan and you get the thing you want, right? And again, you can see vessel here. That's a right coronary artery over here. This is a coronary vein, this big thing there. We can see a double bounce in the mitral valve leaflets here. So you get some really nice pictures of whether or not the valve leaflets are actually coming in opposition. Again, complex flow information is available here. And the interesting thing about this is if that flow structure that we're watching there in that movie did not reproduce itself every beat, it would just be a mess. You wouldn't see anything. It would be artifact up and down this way. It wouldn't be encoded. But so that means that flow structure we're watching there, that swirling is happening every beat, right? On all 12 beats, it looks pretty well the same, right? Because it gets encoded in this. So it's pretty impressive how reproducible these flows are. Again, here's the valve between the right ventricle and the right atrium. What the hell's that one? We can see the septum getting thicker over time here, the left ventricular volume getting smaller. And so for function, and just doing ejection fraction of all chambers and doing myocardial wall thickening and stuff like that, MR is a superstar, right? It does this really well if you get 12 good beats in a row. If amongst those 12 beats, say we had 9 good beats and 3 bad beats, this would look a mess. And because all of a sudden you've got this misinformation about where things are, and it doesn't add up together. Here's a 2-chamber view with, again, the left atrium with that flow. Looks pretty cool. And the mitral valve. Again, this is interstitial fat down here and here. This is all fat towards the apex. This is all fat up here and on here. And so needless to say, MR is a great imaging technique for looking at total fat content in your body. Oh, look at that. That is this thing here. That's a probably primary great cardiac vein, right? And so you can make a nice mapping of where that cardiac vein went from that. So here's 2 short axis images of the heart, left ventricle, right ventricle, liver. This is the chest. This is I want to say a 23-year-old graduate student, 1988, I think this was taken. So, we got good pictures fairly early on. The other interesting thing you can do with MR is you can saturate tissues before you image them. And so what that means is you apply some specially designed pulses, and it will selectively saturate tissue such that when you go to image it, it shows up as no signal. And so when you go to image it, these saturation lines show up like this. And then at end systole, the saturation lines stick to the tissue. So they are truly fiducial markers that move with the tissue. And so now you can measure with great precision things like circumferential shortening by looking at how the distance between these lines change from here to here. That's where they start at end diastole, and this is where they go to at end systole. So this is sort of the gold standard for measuring myocardial strain, because you can measure these lines so well. And so this started in the 80s. We started this at Hopkins probably in the late 80s, I think. And it's still, I think, the gold standard for imaging strain. And so you can just image it at different time points, all in the same acquisition, and get the dynamics of myocardial strain from the MR data. And that can be taken to an absurd extent where this is like super high resolution. This acquisition is done in an animal model. I think it was it's probably I don't know, porcine probably. So 56 time frames across systole, and you get all of these lines throughout the myocardium. And the way you get these reproducible scans is we actually triggered not only to the EKG, but we had a ventilator and we triggered to that as well. And so everything happened at the same, vent phase as well as EKG phase. And so you could just average and get these remarkable high resolution pictures of myocardial deformation. And then there's someone here. Oops. Does this? Oh, it doesn't work. Well, you can look this up. The YouTube's there. This is 4D flow data where these vectors, it's a vector field of fluid flow, and you can acquire this over about a minute, and you get an image of where all the blood is going in the major vessels with 4D flow. It's pretty cool. Okay, so now we're going to look at the technology itself. So this is a picture, of a MR scanner. This is a very big MR scanner. It's probably like a 7 Tesla because you can see how long the magnet is and its size compared to the person. The basic structure is you have a static magnetic field, okay? And it's provided by coils that are wrapped around the patient, and those coils have current in them, electrical current in them. They are bathed in liquid helium such that the material that the windings are made of go into a superconducting mode. So there is no loss or heating with that current. And you get them down to the superconducting temperature, you ramp up the current, and then you just you switch such that you take your ramp your voltage generator off and switch it shut, and it just keeps going, right? So the thing about MR is you have this high magnetic field. It can be 1.5 Tesla, 3 Tesla, even 7 Tesla at this point in the magnet, and it's on all the time. That's one of the risks of this technology, is the fact that the magnetic field is on all the time. So when you walk in the room, or if somebody else who is unaware of that walks in the room, if they have any metallic ferromagnetic devices on, like their ID badge, their eyelets in their shoes, X-Acto knife, something like that, that device, when you get it close to the magnet, will just fly into the magnet at a high velocity. And so while MR doesn't use radiation, there have been fatalities in MR, and those fatalities have all really been accidents associated with the magnetic field, either with objects flying into the scanner or objects pinning people to the side of a scanner, right, such that they couldn't breathe. Or in the old days, they used to use stainless steel clips to clip off aneurysms in people's brain. And so if you didn't have the proper history of that patient and they had one of those clips in and they went in for an MR scan, it was not good, right? Because that clip used to move. They stopped making them out of ferromagnetic materials, thankfully. And so that's not such a big deal anymore. But in the old days, you used to have a head X-ray to make, if they didn't know your history, you had a head X-ray, right? The other thing that causes force and distortion of the magnetic field is blue eyeshadow. So it has chromium or something in it. And so if your patient, all of a sudden their eye sockets are gone on their picture, they probably have blue eyeshadow on. And sometimes you can actually feel the force. And that's okay. So that's the ferromagnetic part. Here they sort of a rogues gallery of magnets. This is an average old magnet, right? A 3T magnet with, you can see the bore is like, I don't know, 65 centimeters or 80 centimeters across, something like that. A 7T magnet now starts to look fairly normal. And these are all experimental systems. Look at the size of this guy and this one, which is a 12 Tesla magnet. The reason you go up in field strength is the polarization or the magnetization you create in the patient goes up with field strength. And so you just get a stronger field. And I think when you do all the math about signal to noise and things like that, I think it goes to the, it's higher than linear in field strength. It's like the 7/4 power for most of the range that we're looking at. But the problem is that as you go up in field strength, the radio frequency that you're using to produce the signal in the patient also goes up, and it gets absorbed more readily at these higher radio frequencies by the patient, and so it'll heat the patient up, right? So they start getting hot because you're irradiating them with a lot of radio frequency energy. Okay, so this is mostly what you'll see in the hospital, either a 3T or a 1.5T scanner. 3T is a large magnetic field. So is 1.5 for that matter. The magnetic field, it causes a compass when you hold it to point north. So we're all bathed in a magnetic field. It's the Earth's magnetic field. And it's a half a Gauss, okay? Which turns out to be, if you convert that to Tesla, because scanners are 1.5 Tesla, 3 Tesla, that's 50 microtesla. So it's a very small magnetic field. You can actually make, people have made images with this field, right? But you're not going to make great ones. And so these magnetic fields we're talking about are really high. What happens, the magnetic resonance, it originally was called nuclear magnetic resonance, and it was discovered in the 40s. It was discovered by 2 independent teams, one on the East Coast and one on the West Coast of the US, one group at Stanford and one Columbia, something like that. I forget. But it is an entirely quantum mechanical phenomenon, right? And what that means is, it turns out that if you have some collection of protons, let's say in water, that's a good way to get a lot of protons together. So we put that in a magnetic field. And when you irradiate that sample with RF radiation and you scan through the different frequencies, there will all of a sudden be a frequency at which that sample absorbs the radiation. It will be at a specific frequency, right? And it turns out what's happening is that the protons, which are a spin 1/2 nucleus, they are affected by a magnetic field, and they can be in one of 2 conditions. They can be in a spin up configuration or a spin down configuration. And so if you took the proton and had a magnetic field and you shot this proton through the magnetic field, it would deflect either up or it would deflect down, depending on which state its spin was in, if it was a spin up or a spin down state. And it can only do one of those 2 things. It doesn't do a continuum, depending on, how the magnetic pole of the proton is angled with respect to the magnet that you're firing it through. If you want to, there's a great set of lectures by Richard Feynman on quantum mechanics, and he uses electron beams as the spin of the electron, because electrons also have a spin 1/2, and so they'll also be spin up or spin down in a magnetic field. And so if you look at his lecture and the Feynman lectures on physics, it's free online now. The whole thing's published online. It's a really good explanation of quantum mechanics based on this. And so it can only be in one of those 2 configurations. So now let's go back to our sample of water sitting in a magnetic field. What turns out is that the magnetic field, if you let the sample come to equilibrium, it'll take about a couple of seconds when you put it in, and now it sits at equilibrium. There is a slightly higher number of protons that are in the lower energy configuration, which means the spins are aligned with the magnetic field, than in the higher energy configuration, which means the spins are opposed to the magnetic field. So that difference in the number of protons that are in those conditions, it's like a thermal thing. Depends on the temperature of the proton bath, etc. But that difference can be used to create a signal from that sample, that water sample. And what you do is you inject radio frequency energy at the frequency when you use the energy of a photon is h mu, where mu is the frequency of the photon. If the photon energy is exactly the right amount to take the low energy proton that's aligned with the field and flip it to the high energy configuration, then your sample will absorb a lot of that radio frequency energy. So we'll irradiate it, like at that frequency specifically. And at 1.5 Tesla, it turns out that frequency is 63.86 megahertz, okay? And that's the magic frequency. So we'll irradiate, say, for, I don't know, 100 milliseconds or let's say 100 microseconds, boom, with a high enough amplitude. And then you turn off your transmit, and you have a radio frequency coil by the sample. And right after you finish transmitting, you listen to the sample. The sample will irradiate back the same frequency. And this is as the protons are going through, flipping back into their steady state configuration, they will coherently do that that flipping will happen coherently, and you will see that as a radio frequency signal. And I have never seen anyone explain it as a quantum mechanical phenomenon and then tie it to the way we're all going to think about it, which is this classical description where we have a magnetization vector that is precessing in the transverse plane. That is a fantasy. It's a mathematical fairy tale, right? That works, right? It's remarkable. But it basically, the magnetization vector turns out, if you look at Schlichter and all of these quantum mechanical books, to be the expectation value of the spin at that in this sample, and it will oscillate, between these values. And that's what you see is this radiation. The way we're going to model it is we're going to say, when we put the sample into the magnet, it will become magnetized. And the way we'll describe that is through a macroscopic magnetization vector. And so we'll say the sample itself is now magnetized, and we have this magnetization vector that is the ensemble of these protons that are in this up or down state. Once you do that, this all becomes really easy, right? It's quite remarkable how the math now works out, so that all we have to do is describe this magnetization vector. And let's say I have a 1 millimeter by 1 millimeter by 8 millimeter bread loaf thing, which is going to be my MR scanner. What our picture will be is a picture of the magnetization vectors inside that volume, the average of them, right, inside that volume. And so you just leave quantum mechanics behind. You don't have to think about it. You just think about the magnetization vector in each voxel, and that's our picture, right? And it turns out it will have an amplitude. The magnetization vector will have an amplitude. Not only will it have an amplitude, it will have a phase. So I can have magnetization vectors on this side of the sample that have a certain amplitude, but they're out of phase by 90 degrees with the ones on this side of the sample, right? So we'll go into the math of how you describe what are we going to use to describe that? We're going to use a phasor, which is just a vector in the plane that rotates, right? And that's e to the I theta, basically. We'll get there. All right, we'll pick this up next time, because all of this is highly technical, and we'll get there. So what did I want to say? Oh yeah, I have achieved acquisition of echo data for patients that we also have CT data. And so I should get together with the team, and we can look at how you will extract the data you need for your project for that data, okay? So if you shoot me an email, we'll set up a time. Any questions about today's lecture? Okay, there is a, it's like a PDF file of lecture notes from a magnetic resonance imaging course I used to give at Hopkins. And it's not that long, it's about 20 pages. If you want a really efficient, short way to look at the magnetization vector and what we're going to be doing and the math, I would read that PDF, right? So I can put that in the announcements as well with a link to that. Okay, cool. Hey, everyone.